So I've got a formula here for us to think about. And it's hopefully very familiar as for the area of a circle. And in the past, when we've seen a formula like this, we've always thought of it as it's kind of a static thing. You pick a value for the radius and you get a value for the area. Or you pick a value for the area and you get a value for the radius, one or the other. But what if both the area and the radius are changing? Right? For example, what if you take a pebble or a rock and you throw it into a stream and it starts making ripples, right? And just think about one of those ripples, right? It starts small, and then it gets bigger and bigger and bigger, and it changes, right? It changes over time. Both the radius is getting bigger at a certain rate, and the area is getting bigger at a certain rate. And those rates aren't necessarily going to be the same. All right, so what I want to do is I want to come up with a way to find a relationship between those two rates, right? To relate these rates together, hence the title here, related rates. Right? I want to find a formula that relates the rate of change of the area to the rate of change of the radius. Okay, so the way we're going to do that, and I'm actually going to explicitly write it. We won't usually do this, but I'm going to explicitly write it this way, just so you can see what we're talking about. Area is a function of time, and the radius is a function of time. And what I'm going to do is I am going to differentiate both sides of this equation with respect to time. Okay, so the left side is going to be d a of t dt equals d dt of this somewhat complicated expression, pi r of t squared. Okay, well, the left side, this is just dA dt. And that's great, because that's what I was looking for, right? The rate of change of the area with respect to time. What happens on the left side? Well, look, first let's bring that pi. It's a constant. Let's bring it up in front. Pi d dt of r of t squared. And this is a chain rule situation, right? I have a composition of two functions. I have the square function on the outside, the r of t function on the inside. So I'm going to use the chain rule. This is 2 pi r of t times the derivative of the inside, d dt of r of t. Okay, so now let's scale this back again, right? We won't make a habit of writing the of t part. We're just going to kind of have it in the back of our minds implicitly. These are functions of time. So now I would write this 2 pi r dr dt. And there is my related rate equation. I have a formula that relates the rate of change of the area to the rate of change of the radius. Okay, so I want to get a little more practice in doing this, all right? So let's see. First, read the question. Suppose that x and y are related by the equation below, and this is the key part that I want you to really catch on to here. X and y are functions of t, functions of time. That's the key phrase that you're going to be looking for in a question to tell you this is not just a regular differentiation question. Right? This is not just a regular implicit differentiation question, although there are going to be some similarities. Right? Instead of differentiating this with respect to x, which is what we normally do, I'm going to differentiate with respect to time. You see that down here in the second part of the question. What is dy dt? And then I'm going to specifically try to find a value, a numeric value for dy dt given these three inputs. Okay, so let's work this out, right? And like I said, I'm not going to do this all the time, but I really want to emphasize this here in the beginning. I'm going to rewrite this x of t squared plus y of t squared equals 9. Okay, differentiate. It's going to be the chain rule on both parts. Right, so this first part is going to be 2 x of t times the derivative of the inside. That's dx dt. Plus, it's really going to be the same thing here, 2y of t dy dt equals 0. The derivative of a constant with respect to anything is 0. Okay, so now again, I'm going to clean this up. Let's just make this 2x dx dt plus 2y dy dt equals 0. And the first thing I was asked is what is dy dt? So I'm going to solve this for dy dt. Let's move the 2x dx dt over. 2y dy dt equals minus 2x dx dt. Now the 2's cancel, right? And let's divide both sides by y. dy dt equals negative x times dx dt divided by y. Okay, now go to that's the first part of the question. That is, what is dy dt? And the second part says when x is, it gives you some numbers, right? And all I'm going to do is I'm going to put those numbers into here, right? dy dt equals negative x is 3, dx dt is 2, and y is 0. Okay, well that's interesting, but this is okay. I mean, this can happen. All I'm going to say here is at those values, dy dt is undefined. I mean, that can happen. It's an entirely legitimate answer. All right. So let me give you one. Right? Try working this one out. It's going to be the same process, right? Be careful of the question. Notice that here you're being asked to find dx dt, right? So that's what you're going to solve for, right? And then you'll substitute some numbers in. All right, so let's see where we end up with here. I've got the log base 3 of xy plus 7 equals 3, and I'm going to differentiate both sides with respect to t. Because again, we've got that same key phrasing here. X and y are functions of t, and then down in the body, right, it starts talking about dx dt and dy dt, which is kind of another giveaway that that's the kind of problem we're working on. Okay, so let's differentiate this thing. Differentiating the right side, this is a chain rule situation, right? So this is going to be 1 over xy plus 7 times the natural log of 3 times the derivative with respect to t, remember, of xy plus 7. This equals the derivative of 3, derivative of a constant. That's just 0. All right, so I'm just going to kind of hold on to this front part. 1 over xy plus 7. That's a 7 there. 7 log of 3 times. Okay, derivative of xy. That's a product rule situation. So this is going to be x times dy dt plus y times dx dt plus 0. Right, derivative of 7. That's just 0. Equals 0. Okay, well, this is actually about to work out nicer than we might have hoped. Multiply both sides by xy plus 7 log of 3. Clear the fraction. Right, the right side becomes x dx dt plus y. See, that was dy dt there. dy plus y dx dt equals 0. And remember, keep track now. We're solving for dx dt. So it's the dy dt part I'm going to move over to the other side. Y times dx dt equals minus x dy dt. and then divide by y. dx dt equals minus x dy dt over y. And that's it. That's what dx dt equals. Right now I can answer the second part of the question, and I'm just going to substitute these numbers in. Right? In that situation, at that particular moment, dx dt equals minus 5 times dy dt, that's 4, divided by 4, which is minus 5. And that's it. Right? So at that particular moment in time, that is how fast the x variable is increasing. Okay, so that's the basic idea, right? So what we're going to do in the next lecture is we're going to look at some physical situations, some practical problems, and see how we can apply this method to them.